Security is not a product, but a process. Welcome to this session on electronic security systems under Module 5, Physical Security. In today's environment, technology forms the backbone of modern security. From access control to surveillance, electronic systems enhance detection, response, and overall protection. In this chapter, we'll build a clear understanding of how these systems work together to create a layered defense. Electronic security systems are a critical component of modern protection strategies. They include access control, contraband detection, intrusion detection, and video surveillance, the four major pillars of electronic security. These systems work together to monitor, control, and respond to threats in real time, significantly improving the effectiveness of physical security programs. In this chapter, we will cover key areas essential for understanding electronic security systems. This includes access control systems covering credentials, locks, biometrics, and authentication methods. We will also look at contraband detection, including technologies like metal detectors and X-ray systems. Further, we will examine physical intrusion detection systems, including sensors and system design, and finally video surveillance, including cameras, analytics, and system integration. Access control systems regulate who can enter or exit a facility. They rely on three types of credentials: something you know like a PIN, something you have like a card, and something you are like biometrics. Security levels increase from single-factor to dual-factor, and then to three-factor authentication, which offers the highest level of protection. Modern systems integrate hardware and software to manage access effectively and securely. Adversaries may attempt to bypass access controls using different methods. Deceit includes social engineering and impersonation. Direct physical attacks involve force or tools to breach barriers. Technical attacks include credential forgery, hacking, or exploiting system weaknesses. Understanding these attack methods is essential for designing stronger, more resilient access control systems and implementing effective countermeasures. Designing an effective access control system requires answering key questions. These include system integration with alarms and video, determining access privileges, handling exceptions, and ensuring compliance with regulations. The system must also integrate with organizational databases such as HR systems. The primary objectives are to allow authorized access, prevent unauthorized entry, detect violations, and protect assets. Ultimately, life safety and egress considerations always take priority in access control design. Personal identification numbers, or PINs, are memorized codes entered on a keypad and often combined with a credential. While they are simple and cost-effective, their security depends heavily on user behavior. Weaknesses include shoulder surfing, coercion, or users writing pins down. Scrambling keypads can reduce pattern recognition, while duress codes allow silent alarms when users are forced to enter credentials. Despite their convenience, pins alone are vulnerable and are best used as part of multi-factor authentication. Different credential types offer varying levels of security and usability. Photo ID badges are common but vulnerable to forgery unless enhanced with security features like holograms. Exchange badges reduce counterfeiting by swapping credentials at checkpoints. Stored image badges allow guards to compare live images with stored data, improving verification. Coded credentials, such as machine-readable cards, support automation, biometrics, and system integration, making them the most advanced and scalable option. Badge technologies differ in cost, security, and functionality. Magnetic stripe cards are low-cost but easily copied. Vegan cards are more secure but still limited. Proximity cards use RFID and are widely adopted for convenience and moderate security. Smart cards represent the current standard, offering encrypted data storage and higher resistance to cloning. Choosing the right technology depends on balancing risk, cost, and operational needs. Smart cards contain embedded microprocessors capable of storing and processing data securely. They are widely used for high-security environments. Hybrid cards combine multiple technologies, such as magnetic stripe and RFID, allowing compatibility across systems. Mobile credentials are an emerging trend, enabling access through smartphones using NFC or Bluetooth. These innovations enhance flexibility, reduce dependency on physical cards, and support modern access control ecosystems. Mechanical locks remain a fundamental layer of physical security. Warded locks are simple but offer minimal protection. Lever locks provide better security and are used in cabinets and safes. Pin tumbler locks are the most common, offering moderate to high security depending on design. Dial combination locks provide strong protection, especially in safes with no reliance on electronic systems. While electronic systems are advancing, mechanical locks continue to serve as reliable and essential safeguards. Master keying allows multiple locks to be opened with different keys while maintaining hierarchical access. This is efficient for large facilities but introduces vulnerabilities. Attack methods include forcing, surreptitious picking, bumping, and impressioning. A major risk is that loss of a master key may require replacing entire lock systems, resulting in significant cost and operational disruption. Therefore, master key systems must be carefully controlled, monitored, and supported with strong key management policies. Electrified locking mechanisms enhance access control by integrating locks with power systems. Fail-safe locks unlock during power loss and are typically used where safety and emergency egress are critical. Fail-secure locks remain locked during power failure, offering higher security but requiring alternate exit provisions. Electric deadbolts provide strong physical security, while electric strikes allow controlled access by releasing the latch. Exit devices enable safe egress in emergencies, and electromagnetic locks offer high holding force but depend on continuous power and proper safety compliance. Biometric systems verify identity based on unique physical characteristics such as fingerprints or facial recognition. Type I error or false rejection occurs when authorized users are denied access, impacting convenience and productivity. Type 2 error or false acceptance is more critical, allowing unauthorized access and posing serious security risks. The equal error rate represents the balance point between these two errors and is useful for comparing system performance, though not always the optimal operating setting. Different biometric technologies offer varying levels of accuracy, cost, and usability. Iris recognition provides very high accuracy but requires close-range scanning. Hand geometry is simple and reliable but less precise. Fingerprint systems are widely used and cost-effective, though quality depends on environmental factors. Facial recognition, including thermal imaging, is advancing rapidly, while voice recognition and signature dynamics are more suited for lower security or specialized applications. Selecting the right biometric depends on the required security level and operational context. HSPD 12 established a government-wide standard for secure and reliable identification credentials. It led to the development of smart ID cards with integrated technologies. UL2 94 provides standards for access control system construction and performance, ensuring reliability and safety. Additionally, building codes such as the International Building Code influence access control design, especially regarding life safety and egress requirements. Compliance with these standards is essential for both security effectiveness and legal adherence. Metal detectors are widely used to detect concealed weapons and contraband. Continuous wave detectors create a stable electromagnetic field and detect disturbances caused by metal objects. Pulsed field detectors send pulses and analyze responses, offering improved detection of different metal types. Proper deployment is critical. Operators should be trained, and dual operator setups are often recommended to ensure both effective screening and observation. X-ray technologies are essential for inspecting packages and identifying concealed threats. Single energy systems are basic and cost-effective, but provide limited differentiation between materials. Dual energy systems improve detection by distinguishing between organic and inorganic materials. Backscatter technology enhances imaging of low-density objects, while computed tomography, or CT, provides advanced 3D imaging for high-risk environments. Choosing the right system depends on threat level, throughput requirements, and operational constraints. Explosives detection is broadly divided into bulk and trace methods. Bulk detection targets large quantities of explosives using technologies like X-ray imaging, thermal neutron activation, nuclear quadrupole resonance, and pulsed fast neutron analysis. These methods analyze density, composition, and elemental signatures. Trace detection focuses on microscopic residues from handling explosives. Techniques include ion mobility spectrometry, chemiluminescence, mass spectrometry, and K9 detection. While bulk methods are ideal for screening objects, trace detection is highly sensitive but requires careful handling and continuous calibration. Detection of chemical and biological agents is critical for high-risk environments. Chemical detection systems often use point sensors for perimeter monitoring, providing early warning. These systems must operate continuously and deliver fast, accurate results. Technologies include optical sensors and ion-based detection methods. Biological agent detection is more complex, as identification often requires sample collection and laboratory analysis, leading to delayed responses. A key challenge in both is managing nuisance alarms, as false positives can reduce confidence and strain response resources. Physical intrusion detection systems rely on three key performance measures. Probability of detection, or PD, reflects how likely the system is to detect an intrusion attempt. Nuisance alarm rate, or NAR, measures false alarms caused by environmental or non-threat factors. Vulnerability to defeat, or VD, represents how easily the system can be bypassed or compromised. An effective system balances high detection capability with low false alarms while minimizing vulnerabilities. Standards ensure reliability and consistency in intrusion detection systems. In the US, UL standards such as UL 639, UL 681, and UL 2050 define requirements for system performance, installation, and classification. European standards like BSN 50131 categorize systems by security grades and define signaling and response requirements. Compliance with these standards ensures systems meet operational, safety, and regulatory expectations across different environments. Exterior sensors can be classified in multiple ways. Active sensors emit energy and detect changes, while passive sensors detect naturally occurring energy like infrared radiation. Systems can also be covered or visible. Covered sensors remain hidden, while visible systems act as deterrents. Detection methods include line detection, which monitors a specific path, and volumetric detection, which covers a defined area. Terrain also plays a role. Terrain-following systems adapt to uneven surfaces for consistent coverage. Exterior sensor technologies vary based on application and environment. Ported coaxial cable sensors are buried and detect pressure or movement, making them suitable for covered perimeter protection. Fence disturbance sensors detect vibrations or cutting attempts on fences. Freestanding infrared sensors create invisible detection zones, but may be affected by environmental conditions like fog or rain. Bistatic microwave sensors provide wide coverage, but require careful alignment and are sensitive to terrain. Selecting the right technology depends on site conditions, threat level, and acceptable false alarm rates. Advanced exterior detection technologies enhance perimeter security with greater precision. Ground-based radar, or GBR, uses radio waves to detect movement over large areas, making it effective for long-range perimeter monitoring and tracking intrusions in open terrain. LiDAR, which uses laser pulses, provides highly accurate detection and 3D mapping, even distinguishing between objects. While GBR is effective for wide coverage, LiDAR offers higher resolution and object discrimination. The choice depends on range, accuracy, and environmental conditions. Effective exterior system design follows key principles. A continuous line of detection ensures there are no gaps along the perimeter. Where gaps are unavoidable, alternate technologies must compensate. Protection in depth uses multiple layers of detection, increasing the likelihood of identifying intrusions early. Complementary sensors combine different technologies to offset weaknesses and improve overall detection probability while reducing nuisance alarms. Clear zones are essential. Removing obstructions improves visibility and system performance, minimizing false alarms and vulnerabilities. Interior intrusion sensors are designed to detect unauthorized movement within protected spaces. Trap detection focuses on high-risk entry points where intruders are likely to pass. Spot detection protects specific high-value assets like safes or sensitive equipment. Channel detection monitors defined pathways such as corridors. Volumetric detection covers larger areas, identifying movement within a space. Selecting the right type depends on the layout, risk level, and assets being protected. Boundary penetration sensors detect attempts to breach physical barriers. Vibration sensors identify cutting, climbing, or impact on fences and walls by detecting disturbances. Electromechanical sensors monitor openings such as doors, windows, or gates using switches and contact mechanisms. These systems provide early warning of intrusion attempts and are often integrated with alarms and monitoring systems for rapid response. Interior motion detection commonly uses microwave and passive infrared technologies. Microwave sensors emit signals and detect motion through frequency changes, covering larger areas and penetrating some materials, but they may be prone to false alarms. Passive infrared or PIR sensors detect heat changes caused by human movement. They are cost-effective and widely used, but can be affected by environmental factors like temperature variations or heat sources. Combining these technologies can improve reliability and reduce false alarms. Dual technology sensors combine two detection methods, such as microwave and PIR, requiring both to trigger an alarm. This significantly reduces false alarms while maintaining detection accuracy. Wireless RF sensors offer flexible installation without extensive wiring, making them ideal for retrofitting or temporary setups. Line supervision ensures system integrity by continuously monitoring communication links between sensors and control panels. These advancements improve system reliability, scalability, and adaptability in modern security environments. Interior intrusion sensors do not operate in isolation. They're heavily influenced by environmental conditions. Factors such as acoustic noise, electromagnetic interference, thermal variations, and air movement can all impact sensor performance. For example, heating systems or sunlight can affect infrared sensors, while electrical equipment may interfere with microwave or electronic signals. Even vibrations or seismic activity can trigger certain sensors. The key takeaway is that interior environments are generally more controllable than exterior ones. With proper planning, such as stable temperature control, minimizing interference, and correct sensor placement, high reliability and reduced false alarms can be achieved. Video surveillance systems serve multiple critical functions in modern security. Their primary role is surveillance, providing real-time monitoring, whether manual or automated. They also support assessment by allowing operators to verify alarms and determine the nature of a threat before responding. In addition, video systems play a key role in forensics, recording evidence of events including what happened, when, and where. Finally, they contribute to risk mitigation by enabling proactive monitoring and early detection of suspicious activity. Together, these functions make video surveillance an essential component of integrated security systems. A video surveillance system consists of several key components working together. First is the scene and lens, which determine the field of view based on focal length and image sensor size. Next is the camera, which converts light into a usable signal. Transmission follows, using cables, networks, or wireless systems to carry the signal. Recording systems, such as DVRs or NVRs, store video for later review. Finally, the workstation allows operators to view, analyze, and manage video feeds. The effectiveness of a surveillance system depends on how well these elements are integrated and optimized for the operational requirement. In video surveillance, identification is typically categorized into 3 levels. Subject identification requires enough detail to clearly recognize an individual, usually demanding high resolution and proper camera placement. Action identification focuses on understanding what activity is taking place, such as detecting suspicious behavior or incidents. This often requires appropriate framing and motion clarity. Scene identification provides a broader view of the environment, helping establish context and location. Balancing these 3 views is essential in system design, as focusing too much on one may compromise the others. Cameras can be broadly classified into fixed and PTZ types, each serving different purposes. Fixed cameras remain in a constant position and are ideal for continuous monitoring of specific areas. They are reliable and ensure critical zones are always covered. PTZ, pan, tilt, and zoom cameras offer flexibility, allowing operators to adjust the view and track movement across larger areas. However, they can only focus on one area at a time. Choosing between fixed and PTZ cameras depends on operational needs, whether consistent coverage or dynamic monitoring is more important. Video surveillance systems can be either analog or network-based. Analog systems use traditional coaxial cables and record video on DVRs. They are simpler and offer more cost-effective, but offer limited scalability and analytics capabilities. Network or digital systems transmit video as data over IP networks and use NVRs or cloud storage. These systems support higher resolution, remote access, and advanced video analytics. While analog systems still exist, modern security environments increasingly rely on network video systems due to their flexibility, scalability, and integration capabilities. Modern video surveillance has evolved beyond simple monitoring to include powerful analytics and intelligent features. Video analytics enable automated detection of specific events such as crowd congregation, unattended objects, loitering, and abnormal movement. These capabilities allow systems to proactively identify potential threats rather than just record them. For example, detecting an unattended bag in a sensitive area or identifying unusual movement patterns can trigger alerts in real time. These advanced capabilities significantly enhance situational awareness, reduce operator workload, and improve the overall effectiveness of security operations. Effective video surveillance system design is driven by clear operational requirements. First, the application must guide equipment selection. Technology should match the specific security need, not the other way around. Second, the primary security function must always take precedence. While systems may support multiple objectives, they should never compromise the core purpose. Third, systems should be designed for future growth, allowing scalability in terms of cameras, storage, and analytics. Finally, regular reviews and needs assessments are essential to ensure the system continues to meet evolving threats and operational demands. A truly effective security framework is not built on isolated components, but on integration. An integrated physical protection system brings together access control, intrusion detection, video surveillance, contraband detection, and alarm communication into a unified structure. Each component supports and reinforces the others. For example, an intrusion alarm can trigger video verification, while access control events can be monitored through surveillance systems. This layered and interconnected approach enhances detection, improves response time, and reduces vulnerabilities, creating a more resilient and robust security posture. Across all electronic security systems, certain design principles remain fundamental. Protection in depth ensures multiple layers of defense, reducing reliance on any single system. Balanced protection focuses resources effectively across all potential vulnerabilities. Complementary technologies combine different systems to offset individual weaknesses, improving overall reliability. Compliance with standards ensures systems meet established benchmarks for safety and performance. Regular maintenance and testing are critical to sustain system effectiveness, while site-specific design ensures solutions are tailored to the unique environment and threat profile. Together, these principles form the foundation of a strong and dependable security system. Electronic security systems form the technological backbone of modern physical security. From access control and intrusion detection to contraband detection and video surveillance, each component plays a vital role in protecting assets and people. We've seen how these systems function individually, and more importantly, how they integrate to create a comprehensive, layered defense. The key to success lies not just in technology, but in thoughtful design, proper implementation, and continuous evaluation. As we conclude, remember, security is not about having the most technology, but about using the right technology in the right way at the right time. Thank you for your time, and I wish you success in mastering electronic security systems.